Thank you, Navya. Today's Bible reading is taken from 2 Corinthians chapter 9, verses 8 to 11. God is able to give you more than you need, so that you will always have all you need for yourself and more than enough for every good cause. As the scripture says, He gives generously to the needy, His kindness lasts forever. And God, who supplies the seed for the sower and bread to eat, will also supply you with all the seed you need and will make it grow and produce a rich harvest from your generosity. He will always make you rich enough to be generous at all times, so that many will thank God for your gifts which they receive from us. This is the word of the Lord. Thanks be to God.
Thank you, ma'am. May I now have the pleasure of inviting you, sir, with virtual greetings.
Thank you. Thank you.
Thank you, sir. It gives me immense pleasure to introduce our eminent speaker for today, Dr. Jitendra Kumar, sir, Professor and Head Department of Mathematics, Indian Institute of Technology, Ropar. Sir completed his Masters in Industrial Mathematics from IIT Roorkee and then from University of German. Sir was awarded doctorate degree in 2006 from Otto von Guericke University, Magdeburg, Germany. Sir worked as an assistant professor from 2009 to 2014 and as associate professor from 2014 to 2020 at IIT Kharagpur. Currently, Sir is working as a professor at the Department of Mathematics, Indian Institute of Technology, Ropar, Punjab. Sir is a recipient of several recognized awards and fellowships, including the Alexander von Humboldt Fellowship, DGF scholarships, etc. Sir has published more than 100 articles in highly reputed international journals. Sir's research interests are numerical solutions of integral differential equations, numerical analysis, modeling and simulation of problems in particular systems. I now take this privilege to invite Dr. Jitendra Kumar, sir, to kindly take over the session. Over to you, sir.
Thank you, madam. So for this nice introduction. So am I audible perfectly, right? There's no issue?
Yes, sir. Yes, sir.
Yes, sir.
Okay, great. So let me just share the screen and then we will start. So, okay. Yes. So I think my slides are visible now.
Yes, sir. Yes, sir.
Okay. Perfect. So thank you very much again for the invitation. So it is my pleasure to talk on some of my research, and then I thought of, because this is a mixed crowd where I think bachelor's students and master students and some PhD students will be joining. So I will try to not just to discuss my research, but those research part I will take as an examples from the applications, but I will try to introduce that what do we mean by mathematical modeling, what are the steps we carried out in the mathematical modeling part, and what are the challenges and opportunities. So those part will be about 20 to 30 minutes, and the rest I will show some applications from real life. Okay, so this is just an overview of the talk. So I will, as I said, will focus on this mathematical modeling part mainly. So this will be interesting to all of you at all levels. So even for bachelor's students who are doing just their BSc or BTech. And then there will be some real life applications which will be well understood with all challenges and opportunities, which I will discuss as a very basic, with the help of a very simple basic example in the introduction part. Fine. So let's come to this mathematical modeling part. So some of you who are not much aware, they can learn something, and those no, for them it's going to be very basic. So they can just skip this part basically. So this mathematical modeling, when we talk, just a minute, yeah. So this is the applications of mathematics to real world problems. So mathematical modeling comes into the picture when we try to predict something from the real life applications with the help of mathematics. So just an example to understand the whole process and what are the difficulties during the modeling or the simulation process. We take an example. Suppose we have we want to study the growth of bacteria in a flask where we have unlimited supply of nutrients. So just to simplify the problem. So the question comes that why do we want to do this mathematical modeling, and what do we want to determine from the model? So the answer to the first point, why do we want to have mathematical modeling? So the reason is very clear. There are several actually. So one of them is doing various experiments are very expensive and sometimes very time-taking. And in some cases, it's not possible, in fact. So we want to have a mathematical model through which we can predict the future, in many cases, what will happen in future, or in some cases that what will happen if we change these parameters and so on, what will happen to the experiments, which are sometimes very, very expensive to do. So these are the objectives. And what do we want to determine from the model? Of course, that will depend on what we want to model, but that will be also clear from this example itself. So the modeling process. So what are the steps we follow in the modeling of various real life applications? We have seen recently, I mean, the last 2 years was, we were going through this COVID situations, and there were many mathematical models were used to predict the behavior. And if you were following, none of them basically predicted well at what will happen in next 6 months or next few months. So it is not always easy to predict something which is reliable. So there are many challenges, but still we try, and in many cases we are successful also. It is not always a case of failure. In fact, in COVID situation also, there were, at least we were getting some idea that when the peak will come, when it will go down, and so on. So there were some predictions which were also helpful. So what do we have as a process in this modeling? So first we need to closely observe the process, because without knowing the process well, we cannot think about the modeling, because there we have to capture the kinetics of the underlying process. So understanding the observing the process is of course very important. So for example, if we just go to our example here, we observe. Yeah, sorry, is there any problem? Am I not audible? So there were some issues.
Sorry for the disturbance, sir. I've muted that student.
Okay, so okay, then it's fine. So there was no such issue. Okay, fine. So I was to the point here that we need to observe the process before we start modeling. So observation, for example, in this case, could be that we observe the growth of the bacteria for a few days, if we have the possibility. So like suppose day one, the number of these bacteria were 1,000, and then this is a hypothetical example, so nothing to do with the reality here, just to understand the modeling process. Day one, suppose it was 1,102, day two, it was 1,213. So we observe a little bit about the population of the bacteria, and then we realize, okay, day one population, the population in day one is increased by 10102. So it was now it's 1102. Fine. Day 2, it was increased by 111. And by this, just very few data we have available. So we make understanding that, okay, change of population per day is like population of that day. And if you multiply by 0.1, we will get this change. So roughly in 1000, so you have 0.1 means 100 change. Here we have 1010, 1102. So if you multiply by 0.1, we will get roughly 110. So this is observed here, that change of population per day is happening. The change of the population of that day, and if you multiply by 0.1, that is the change we are observing here with this simple data points. Now we need to observing, so that was the observation of the experiments. And now we go to the mathematical model part. So we have to define the variables and the parameters. We have to see what is of our interest, which we want to predict. For example, we want to predict the population of bacteria at the beginning of day n. We need the initial population of the bacteria, which is denoted here by x0. N will denote here the time in days from the present. So n0 means, x0 means the beginning, x1 means day 1, and so on. R is the growth rate. That means the change of population per day per bacteria is happening. So we have to think, I mean, this is in a simple scenario, and just by observing, we thought that these much variables are enough now to predict the behavior of the population of the bacteria. But as I said, these are just some parameters, very simplified model, and it may not predict the reality accurately. We will see in a minute that what will happen. So we start formulating the model based on our observation. So we have to make several assumptions when we translate the real life problem to the mathematical world. So that means we ignore the temperature, the effect of the temperature. We ignore the size of the flask because that may be also limited. We have here limited several things. So some of them, like I mentioned, the temperature, the size of flask, and many more. We have also assumed now, or we are assuming like the constant growth rate, that whatever the growth is happening in the population per day per bacteria, it remains the same, but which also is not the reality, because when there are more bacteria, then there might be some other constraint where the bacteria growth will be slowed down, and so many things can happen. So we have to basically, the point is we have to make various assumptions to convert that real world problem to the mathematical world. As a result, we try to formulate very basic model. So we say, okay, the growth or the population on day 1, so x1 will be x0 plus r times the population or the initial population, where r is that rate which we have observed before from the experimental data. It's 0.1, which we are assuming again that it will remain as constant. X2 will be x1 plus rx1, and so on. So this is our discrete model. This is the mathematical model. We have a very simple mathematical model of that problem. Always the real life problems are very, very complicated, though they may look very simple. But when you try to model through the okay, so this is the discrete model we have. And then again, there are two ways. So one, we have the discrete model where we assumed here the population on day 1, population on day 2, and so on. But population of bacteria is increasing continuously at every moment. So we can, instead of having such a discrete model, we can also have the continuous model, for example, right? So as discrete model, we have the continuous model where we are saying that it will be like dx over dt, the rate of change in this population of the bacteria will be equal to that growth rate and multiplied by the population, which is also happening here in the discrete model. So we can have a discrete model, we can have a continuous model. Sometimes we first get the continuous model, which again is difficult to solve, and then we will get out of this discrete. We will use some numerical techniques to again discretize this. So there are two. Yeah, so are there some issues? Am I audible there to everyone?
Yes, actually, there is one student. She's unmuted herself, and I have removed her from the meeting.
Okay, okay, fine. Maybe he wants
Sorry.
to ask something, or I don't know.
No, sorry for the disturbance.
Oh, no issues. Okay, so that we deal daily almost with the students, so no issues. Okay, so we can have discrete model directly from the given process, from the given real problem, or we can have also continuous model. These are the mainly two possibilities. So the first step was understanding the process. The second was converting with various assumptions to the mathematical model. Now we have the solution. So another challenge comes in many cases, that how to solve the underlying models, whether it's a discrete or continuous. In either case, we have problems. So here the solution is much easier. So from x2, you are getting x1 plus r x1 and so on. So you can substitute again x1 here from the first equation and so on. So what you will get finally, xn in terms of the initial population. So initial population is known, and then the r is known, and then you can get whether x10 or x20 from this discrete equation. So directly, this is what we are calling the solution of this system or this model. Similarly, this is a simple ordinary differential equation. We have the initial condition. That means the initial population is already given to us. It was x naught. So we can solve this differential equation to get our solution. X is equal to x naught e power rt. So this is r here, e power rt. So we can have the solution of the discrete model. We can have the solution of the continuous model. In many cases, when our model are very difficult, it is also very difficult to get the solution. And usually in all application problems, we try to approximate the solution also through some numerical techniques. So having the exact solution of the given problem is rare. The next step comes to the validation of the model. So once we developed our model, we have to test whether the outcome, the prediction of the model is correct. We try to do in this case, for example, that discrete model, we have evaluated the population up to this day 9. Similarly, with the continuous model, in each day we have evaluated. And then there, for the validation, you need some, again, the experimental, the actual values, what is happening in reality. And then you will realize, okay, you were good at the beginning, you were good here, you were well, not so far. And then slowly you see that your model is, whether it's a discrete or continuous, it started over predicting. It was not, the growth was not much as compared to your mathematical model is predicting. Your mathematical model says on day 9 it will be 2459, where the reality says it will be, the reality tells, your experimental tells it will be 1800. So the difference is growing much. So that means there is some problem in the model. Yeah, so we cannot use this model, because if you predict after 30 days, the situation will be worse. Meaning, if you just try to plot this result, the discrete model we have formulated with respect to the days, you will see this is the behavior of our model. It is increasing like anything, exponential increase. So after 50 days, it will be a huge population. But our experimental result says it will not be as much as we are getting from our model. That means some corrections are required. So that means, which we call the model refinement. So you have to refine your model to make it more realistic, just looking at this validation step. So you have to change now the assumptions of the model. For example, it was a constant growth. So perhaps it is not a constant growth, because after sometimes the growth is less as compared to at the beginning. That means you have to refine your model. So now, instead of that constant term in our model, we have restricted with this 1 minus x naught over k. This k is some restriction parameter. We have introduced some parameter which will restrict the growth. It is greater than this x naught. So this 1 minus will be smaller than 1, which is multiplied by r. So your growth rate will reduce here. So like x1 will be more, but x1 minus x1 over k will be less. So over the days, the growth will be restricted. So we have just refined the model to again predict our experimental results. Similarly, the similar changes we have to do in the continuous model as well. So the simplified model, which was not realistic, but if you plot now this one, the refined one, where you have restricted your growth, you will see the behavior here. It is not exponentially increasing, but you have some decay after some point, and then you can see this kind of steady state will arrive after a few days. So which looks more realistic, but this is what I said, under many assumptions. Of course, this will not predict the real behavior. You have to include many other parameters in your model. This was just to give you an idea that what kind of steps we do when we formulate a mathematical model. So the modeling process, you have the model, whether it's a continuous or it's a discrete model. What are the challenges? I want to just refer here. So this hypothetical example is over now. I will just summarize the challenges, and we'll go to some more real life problems and applications. So here, the first challenge is the formulation of the right model. Of course, it is difficult, not so easy. In many cases, the solution of the underlying models, you have nonlinear ODEs, PDEs, and system of PDEs and so on. Again, very difficult to get the solution once you have the right mathematical model. Getting experimental data for the model validation is another challenge, because sometimes it's not easy to perform those experiments, or they are very expensive, or getting the measurement out of this experiment, the exact measurement is difficult, or measuring several quantities is impossible. So there are several challenges here as well. Then what we have, finding modeling the right parameters. I mean, in your mathematical model, you have many parameters. Like in our case, it was R, it was K here. So what should be R? What should be this K? Again, you have to choose these right parameters depending on your experimental data or your physics of the problem. You have to model, or you have to fit these parameters. And another is, in many cases, is the computational time. So sometimes your mathematical model is too complicated, and solving itself is taking months or years. And that is another challenge. So you have to see that how to make your mathematical model efficient. Yeah, so time efficient. So that is another challenge. So these are the few challenges I have mentioned here. There are many more when we talk about the mathematical model and simulations. So this just to give you a basic idea that how complicated this modeling process overall is from the formulation.
Sir, can you unmute yourself, sir?
Oh, so I was muted there. Okay, fine, good. So what I was saying before, that there are various challenges, yeah, starting from the formulation of the model to the computational time. At each and every step, there are difficulties, there are challenges. So just to summarize the flow chart of this mathematical model, so we have a physical problem. Out of this physical problem, you look for the physical laws, make some assumptions, define variables, parameters, and so on. Then you formulate your mathematical model depending on your physical problem. Well, once your mathematical model is ready, then either exactly or approximately you have to solve, you have to find this mathematical solution. And then with this solution, you have to also interpret the results to the actual problem, and basically finally going for the model validation. Yeah, you have to look for the model validation. If your results are satisfactory, then you are done with your process. And in many cases, you will see the results are not satisfactory. You have to again visit to define your assumptions. You think about whether which assumptions you can relax. Probably that is important, but you have assumed there that this is not important, and you have to maybe define more variables. You have to look for more physical laws which are actually crucial for this mathematical model. So this is the cycle here, which you have to perhaps go through several times. And then finally, you will see that, okay, you have some satisfactory result, which are useful for predicting that particular process parameters. Well, so I will just now from here with the basic introduction, I will move to more real life problems, more challenging problems. So here I'm talking about in particular modeling of particulate processes. So I'll give you just a short introduction that what we do, what is of interest there, and what are the challenges and how do we overcome those challenges. So here a system where the large number of particles interact and change their properties, we call that particulate process. So for example, you have seen in the food industries, several such products, whether it's a soup, whether it's a coffee powder, or it's a sugar granules, or in the chemical industry, you have detergent fertilizers, or in the pharmaceutical industries, you have granules again, like capsule, tablets, and so on. They always you will find them or these granular form, yeah, not in a powder form. There is a reason for this. When we form such products, there are several mechanisms happen. One is called the aggregation, where the very small powder size particles in presence of some liquid binder, they meet each other and then we form, which I'm calling granules, yeah, so the bigger size particle. In this process, when we are doing this, trying to make those powders bigger size particle, always the breakage will happen. And in some cases, this is unwanted process when we want to have the granules of bigger size, but the breakage is happening continuously. So this is what unwanted for this particular process. But sometimes we do want to have breakage, and then this is not unwanted, this is wanted process. So in several applications, we want to produce actually small size particles. When the paint, for example, is you have a nano size particle, you want to have a nano size particle, and then many other this nanoparticle technology, you can see where our aim is to produce small size particle, where the breakage, this mechanism will happen. The growth, where the particle like granules will receive these non-particulate material. So, but material in the solution form, it will stick to the surface and it will be dried, and the particles will simply grow and grow. So that is called the growth process. And also the nucleation. So in the process, the appearance of the new particle by whatever under several influencing parameters. So we have the appearance of the new particles, which we call at nucleation. So these are the these are some of the important processes which actually happen when we produce such granules. Well, why do we produce granules? You will understand from this simple video here. Perhaps these are visible. So here we will pour the powder here in the stirring water. So you will realize that just the coffee powder. And what you will realize about the mixing here. So you can see, perhaps you don't see very well what is happening inside, but I will tell you. Now in the second experiment, what we have done, in the first one, actually it's a very bad mixing. You can see even on the top, the powder is there. Also inside, many lumps are formed because of this powder. Now, what we have done, instead of putting this powder, and that's the result, like you have the coffee not in the powder form, but in the granule form, because you put in your hot water or hot milk, and then you just stir and it will be dissolved. There will be no loss of, or there will be no lumps formation. So if we do here, if we add, for example, this granules form, the same powder in the granules form, what will happen, you will realize here, which is perhaps not very visible from this small picture, but it's very well mixed now when we have put in the granules form. There are ways how to form those granules out of that powder itself, and I will be talking about a little more on that. So here we have a very good and fast mixing as a result. And that's the reason you see all these things in granule form. There are various other advantages having those in granule form rather than particle, because these granules flow better than the powder. And it's very useful property when we have this pharmaceutical tablets formation. We have the dust-free handling, because if you transport the powder, there will be loss certainly. So here we have the dust-free handling, better solubility than powder. We have seen in this experiment itself that the powder, the solubility was an issue. And here we have a nice solution at the end through this granules. There are many other, the transport is easy, and the segregation prevents and so on. So there are so many advantages of having the granules instead of powder. Well, what is important here is the particle size is very important, or particle size distribution is very important. This is what we are looking from the mathematical point of view. And usually in all these processes, we want to have a uniform size particle. We don't want to have a very large size particle at the same time the powder-like particles. No, we want to have a same size particle with some desired size, depending on upon the applications. So coming to the equations for this. So this is the mathematical model, which I will not describe in details how it is coming, how we have formulated this model, but this accounts for the aggregation and breakage in a well-mixed batch system. So the system is well mixed. It will not read the space dimensions, so everywhere the same situation, but it will model the aggregation and breakage process. Basically, the first two terms here, the integral terms, will model the aggregation phenomena. The second one will model the breakage phenomena. So only these two I'm considering here for demonstration. And this is just the one-dimensional model I have considered, where what do we mean by one-dimensional? Only this X is the size, is the volume, let's say, of the particle is being considered. So this F is the number density, which will tell you that this size of particles at particular time t are how many in the system and how it evolves. So this will tell you the solution of this mathematical model will give you the particle number density distribution. At the beginning, you have maybe very small size particles. So in the beginning, you may have more small size particle and less big size particle. So it is volume here, for example, and here is the density. Maybe when the aggregation is the dominating phenomena, so the particles are becoming bigger and bigger. So you will have the larger size particle more, where here it was a smaller size particle. So as the time evolves, and if aggregation is your main phenomena, then what you will see after some time that, okay, now the particle size has become, particles have become bigger, and usually we aim for very narrow size particle, yeah, not very wide distribution. So all these with these objectives. Now the crucial part, because these model equations are very generic, they can model any phenomena where the aggregation and breakage is happening. But the problem is, depending on that particular process you are modeling, there are these unknown parameters here. This is beta in the first equation, then here we have B, S, and this S again. So these parameters, these kinetics parameters have to be modeled for that particular process, for that particular application. That is really a challenge, that you have to model all the physics of that particular process in the form of these betas and B and S. So those are the challenges here, to simulate those processes to predict this particle size distribution for a particular experiments. Another challenge, so first let me just write here that what are the quantities of interest. So of course you want to get here F from the equation. We want to also get here the total number of particles. So not if this information is not available or not possible to get out of here, at least we can get the integral of this, so the integrated information, which is easier to get out of those equations. Or this total volume, when it is multiplied by X, we are interested to get. And we are also interested in general, which we call moments. So when we have, these are the integral properties of this F. So sometimes the actual, the prediction of this F accurately is not possible, but then we will see whether we can predict at least this information accurately out of it. So the first challenge is how to solve these equations. So this is just a one-dimensional case I'm going through quickly now. So again, when we the question comes how to solve it, there are various ways we can look at it. So this was the given equation which we have modeled there for those processes. Mathematically, we have also observed that this equation can be written in this compact form, where this F is given again with this double integrals. But the benefit in this equation is that there are various suitable numerical schemes which can directly be applied on this form, not on this form there. So therefore, this is also interesting to see this problem in this form. But there are various problems which comes when we apply numerical scheme to this compact form or this compact form. So I'll just briefly mention this and proceed further. So this is the usual process when we have this continuous equation which is not solvable exactly. We go for the numerical one. So we discretize the domain, and then there's a process. If you are not much familiar, you can skip this one. So we discretize these equations so that we have now the information we can get at discrete level only, not for all volume. For example, we can have those information for certain discrete volumes, and then we can solve those discretized equations. Finally, we can get the solution, the approximate solution of the given problem. So there are many issues when we have applied directly on that one compacted form, for example. So there were various challenges. Finally, the result also for one particular case I have presented here. For example, this was the prediction of the total number in the system when only the breakage is happening. So breakage means the total number of particles will increase over time here. So this is also, you can see, not matching well. And also the number density, also there are a lot of error. So further issues, it's also expensive when we go for 2 or 3 dimensions, because in one dimension itself, you will see that those double integrals, handling them is really difficult. So we thought of that we can directly handle the equations that given in this standard form before without in this compact form. Again, we try to solve the problem directly by the usual process of discretizing the domain, then integrating over the domain and so on. And what we realized that after this, that is discrete, the equation of the discrete, the solution of those discrete equations now, they do not follow the mass conservation, because our original equations, when we have breakage and aggregation, they were mass conserving. Yeah. So if we are talking about the closed system, only the particles are getting merged to each other, or they are getting, breakage. Due to breakage, the particles are born there. So, but the total volume remain constant because we are not adding particles from outside, or there's no particle generation inside. So, but our numerical solutions does not conserve the total volume or the total mass of the system. That is another big challenge, that how to do that. So again, you have to look for those challenges. So here, for example, this was the mass which was supposed to be constant over time, but this numerical scheme is not following this. Though the number prediction is very well, the total number were predicted very well for this aggregation problem. So in the aggregation problem, for example, the total number will decrease over time. And then the challenges come that what to do now. So there are problems in this. So we have done some fixes here. So we try to get some weights in each these equations so that we can fix the problem of mass conservation, which was fixed here. And then you see that the mass is conserved, but then the deviation with the total number started. So one problem you fixed, and then the another one started. So we have fixed the second problem as well by putting some more weights, cleverly chosen weight, so that everything remain intact. And finally, we have a nice numerical method. So we have done some mathematical analysis also to prove all these, that the solution of this equation will actually predict the actual solution nicely. So that was the one part where we look for the solutions, which I said when we have mathematical model, we have to look for the solution, the numerical solution. So that is also challenging in many cases. Then comes to the modeling, because those equations are very generic, and then you have to model those for a particular experiment. So this is just one example I'm showing you. This is the so-called fluidized bed granulator, where we produce those granules which I was talking about before. So here that powder is set here, and then with the hot air, which is fluidized, which fluidizes these particles. So the hot air passes from this distributing plates, and this powder will be fluidized there, and then within the presence of this spray binder, these particles will start growing, and then we can take them out of this system. So there is an aggregation process mainly in this. That means this equation, we can predict the particle size distribution over time in such an equipment. We also tried, and many other researchers do so. So they assume some form of this beta or this kinetics parameter, which we have to model for this particular experiment. And this is not that we this just based on some random selection, but there are certain physics to choose those models. But still, what is happening that we have to just fit this beta naught A, B, depending on the experiments we are trying to predict. So this is what by the fitting. So we have chosen this beta cleverly, this A and B, and then those equations are predicting our results, which is coming from the experiment. Well, similar type of modeling was done in another experiment where the aggregation and breakage both was active. Again, lot of this beta has a lot of fitting parameters. So this experiment was different now, and the beta has chosen differently because that will not work, which was earlier there. So again, depending on the process, we have to see that we have to closely observe the physics and then think about the modeling part. Again, here in D also, there are various fitting parameters. So these models exist already in the literature. Many researchers, before they try to set the behavior of these beta for those particular kind of process. But then for your experiments, you have to have these parameters, you have to fit these parameters. That is the problem in some sense. I will explain you. So then you can predict your experiments well. But the problem is that if you change your experiments, then you have to change your parameters again. So basically, you are not predicting something new. You are just predicting your experiments, which you have already. So then what is the use of it if you need to fit so many parameters? This is the questions we asked ourselves. And then we tried to we have proposed, or we have changed the modeling approach a little bit, that this modeling approach where we have so many fitting parameters, which I am calling here the traditional approach, is not suitable actually. So we now try to observe the whole process. For example, the first I mentioned you this fluidized bed process. We observed very closely that what is happening here. So that these particles are receiving and so on, and then whether these under the droplet, another particle hit exactly at that droplet, there is a chance of the aggregation, or it may again rebound, or so many things are happening. So we try to capture look at each and every detail of this. And then we thought of that, okay, this beta should have at least those initial many parameters, influencing parameters. We try to push it here. So with this probabilistic approach, we have taken that whether wet collision will happen or not. If it is wet collision, wet means both the particles are wet. A wet dry means one is wet, another is dry. So all those possibilities we have taken, and as a result, we have a much more complicated result for this beta. So this everything, whatever appear here, we try to model separately. So overall, the model has become very, very complicated. But now it is not like based on the fitting, but based on various other parameters which you can change and still predict the results. So there are still work going on. It's not completed yet. And I am just showing you that we have some results which are much better than the earlier one in terms of the generality. Here, another experiment. I think I have 10 more minutes to finish, right, ma'am? So
Yes,
shall
sir.
I continue for another 7-8 minutes, right? Okay.
Yes.
Okay, fine. So this is another one where we have the fragmentation problem. So the problem is of the breakage here. So this is called sonofragmentation, a technique which is used for particle breakage using ultrasound. Because those pharmaceuticals crystal are very delicate, and there is a special techniques to break them. You cannot just have some milling operations on them. The properties will change. So this is through ultrasound. Ultrasound will create basically the bubbles there inside the medium, and then those waves will hit, and finally we have the breakage. So these experiments were done in the chemical engineering department in one of my colleagues' lab. And so this is the pharmaceutical crystal called pyrazinamide, and this is used for the treatment of tuberculosis. So it's also expensive material, and we were studying that whether we can predict the particle size distribution with our mathematical model. So first we observed what is happening in the experiments. So this was like initial size particles, then we have after breakage and so on. So you can see the breakage is happening from here to here, and then after 60 seconds, 90 seconds, very small particles. So we need to observe this closely, that what is happening. So the crystal breaks, basically we observed that randomly somewhere within some specified region. So that was coming from the experimental observations and measurements. And the crystal, we have also observed the crystal with length lesser than 20 micrometer do not participate in the breakage even further. So all those observations we had, and then we made several assumptions based on those observations, and we tried to now put under those assumptions our modeling. So this was the breakage equation, which I shown you in the beginning, but it's in 2 dimensions now. And those parameters which are there as B and S, we try to model again, looking at the experimental observations. And then we try to predict the experiments. So this is the results from our equations. These are from the experiments. And there is hardly any fitting parameters here. So we can independently predict all those results where the experiments are really expensive. So these are some results which you can see we have predicted with this equations with these mathematical models. So that is something very was very challenging but interesting at the end. So I think I can just complete it here, because the next phase, again, we have a different kind of modeling and several problems from pharmaceutical industries, which will take another 15-20 minutes. So I think this is the right time where I have given you some idea that what kind of issues we have in mathematical modeling, what is mathematical modeling, and how do we face those challenges, resolve those issues in mathematical modeling. So I thank you very much for your attentions. Yeah, so thank you so much.
Thank you, sir. Thank you.
Thank you, sir.
Thanks.
Thank you, sir.
So if there are some questions, so I'll be happy to answer. Yeah. Sure. So are there some questions if someone wants to have some more idea?
I don't think so.
Okay, great. Yeah. So I hope it was useful to some extent, at least some idea people got about the mathematical modeling who are not familiar with the modeling part.
So regarding this graph, may I know what kind of programming was used?
So we used MATLAB only, nothing more. So all these evaluation computation was done in MATLAB, whatever I have shown in my.
Okay, sir.
Yeah. So it's our own code, no software, just the MATLAB we have used to solve those equations there and so on. Yeah.
Thank you. Thank you, sir. On
Thank you
behalf
so
of Department of Mathematics, St.Ann's College for Women, I would like to express my sincere gratitude to Dr. Jitendra Kumar, sir, Professor and Head Department of Mathematics. Thank you, sir, for accepting the invitation and gracing the occasion this evening to share your expertise. And thank you, sir, for explaining about mathematical modeling in depth with real-world examples. We understood clearly about the growth of bacteria in flowers and differences between computational and experimental results. And also emphasizing on one special topic, sonofragmentation using ultrasound.
Yeah.
Thank you so much, sir, for your time. And I thank Head Department, Dr. Remla Xavier ma'am, for giving me this opportunity, and all my lecturers for constant support, and all the participants for their attention and cooperation. Thank you, each and everyone. Thank you, sir.
Thank you. Yeah, have a good evening. Thanks.
Yes.
Thank you. Thank you so much, sir.
Sir, may I
Yes.
request all the participants to switch on their videos for a photograph? I request all the participants to enable their videos for photograph. Thank you, sir. Thank you, ma'am.
Okay. Thank you. Yeah. Thank you all. Thanks.
Thank you, sir. Are you sharing the feedback from?
Yes, ma'am, I'm sharing. I'm sharing. I request all the participants to please fill the feedback form.
Who was that Kirtana Navya? She was making so much of noise.
I don't know, mom. She's not from my class.
3
I
times.
removed her.
No, 3 times I removed her and finally I muted everyone. I was like fed up.
Ma'am, so far I received 30 responses.
Hmm. We'll wait for another 5 minutes more.
Yeah, ma'am. We'll wait.
shall we leave the meeting?
Do I end for everyone, ma'am?
No. Feedbacks. Got the feedback, Navya?
Almost done, I think, ma'am. Only 10 participants.
Navya, unmute yourself and talk now.
Sorry, ma'am. Ma'am, I received 40 responses.
40.
Mm.
Shall we end, ma'am?